So a ladder 26 foot long is leaning against a vertical wall, and if the bottom of the ladder is pulled horizontally away from the wall at a uniform rate of 2 feet per second, what is the velocity of the top of the ladder when the lower end is 24 feet from the wall? Okay, so this is different than last week's word problems because it says, what is the velocity? It doesn't say, what is the maximum or what is the minimum? It just says, what's the velocity? So that's why it's in a different section. It's a different kind of problem. Okay, so we're going to start out drawing a picture. And we've got a wall and the ground. And then there's a ladder leaning against the wall. And then a little bit of time goes by, right? We still have the wall, we still have the ground. Those have not moved. But later on, the picture looks like this instead. Because the ladder is falling down. Okay, so at first the ladder starts pretty far up on the wall, and then later the ladder is farther down on the wall. In both cases, the ladder's length hasn't changed, so that's 26 feet. So it's okay to mark that as 26, because that's not changing. But any quantity that's changing, you need to mark as a letter. So I'm going to have y represent the distance from here to here, from the ground to the top of the ladder. And here y is pretty big, but here y is smaller. And then I'm going to have x represent the distance from the bottom of the ladder to the bottom of the wall. And here y is small, but then when the ladder falls down, sorry, here x is small, but when the ladder falls down, x is getting bigger. Okay, so it's very important that those stay as variables. Okay, it does say in the problem that it talks about when the lower end is 24 feet from the wall. See that in the last sentence? It says when the lower end of the ladder is 24 feet from the wall. So that's talking about this being 24. And so a big mistake that a lot of people make with these problems is they label this as 24, not x. But you can't do that because the 24 is changing. Here it's not 24. So it's very important that you not use this till the very end of the problem. So just to emphasize that, maybe put a slight X out. I mean, we're going to use the 24. It's a good piece of information. We just can't use it yet. The 26 is solid. It doesn't change. So we can use the 26 throughout the whole problem. Okay, so is there a formula that applies to both of these pictures? Yeah, the Pythagorean Theorem, right? There's a 90-degree angle here. So that means in both of these pictures, the x squared plus the y squared is going to equal the 26 squared. And this is a useful equation, but it's got some limitations. The limitations are that it either applies to this picture or it applies to this picture. But it doesn't apply to both of them at the same time. If you know what this x is in this picture, you could figure out this y. Or if you know what this x is in this picture, you could figure out this y. But you can't figure out how this picture is changing into that picture. So this is a good equation, but it has limitations. It's called a static equation. And the reason it's called a static equation is because it doesn't change. Nothing in it is changing. X is a number, y is a number. Okay, but our problem is talking about how things are changing. So the problem says, what is the velocity of the top of the ladder when the lower end is 24 feet from the wall? So the problem wants to know how things are changing. So this equation is not going to do it for us, because the problem's saying how quickly does this go into this? What's the velocity? Okay, so in order to change this equation, which has limitations, into something that we can use, we're going to take the derivative of it. So d over d means take the derivative, right? So that's what I'm marking down over there. I'm leaving the bottom blank temporarily, because I want to talk about what goes there. Usually it's d dx, right? Because we're taking the derivative with respect to x. Okay, but this time there's an element that's not involved in the problem. The question is, well, the rate that's given talks about 2 feet per second. So that's talking about how things are changing as time goes by. So the time needs to get introduced into this somehow. And since things are per second, then we're going to differentiate with respect to time. So it's d dt. So that's kind of weird, because there's not even a t in this equation. But we're trying to introduce the variable t, because we want to know how things are changing per second. All right, so we're going to take the derivative of this. And since it's d dt, both of these letters are disguised chain rule. Because if it was d dx, then this would not be, but this would be. But since it's d dt, they're both disguised chain rule. So when you take the derivative of y, it's 2y, y prime. And when you take the derivative of x, it's 2x, x prime. So that's kind of weird that x is a disguised chain rule. But it is, because we're talking about per second. And then, of course, the derivative of that number is 0. So this new equation is called a dynamic equation. And dynamic means change. And so this is an equation that's going to be useful for us, because it's an equation that talks about how things are changing. Okay, so let's see. We've got some other information. We got the 2 feet per second, right? It says if the bottom of the ladder is pulled horizontally away from the wall at a rate of 2 feet per second. Okay, so the bottom of the ladder is pulled away from the wall, so this is moving at 2 feet per second. So when the bottom of the ladder moves away, that makes x bigger, right? So x is changing at 2 feet per second. So that means the x prime is 2 feet per second. Because x prime is the change of x. It's the derivative of x. So since the bottom of the ladder is moving away at 2 feet per second, that means that the x is getting bigger by 2 feet per second. And then that means x prime is 2 feet per second. So I can come over here and figure out, well, I don't know x yet, but I know x prime is 2. Well, actually, the problem did tell me x, right? The problem told me 24 for x. Because it said the bottom of the wall, when the bottom of the ladder and the bottom of the wall is 24 feet away. So that's what goes there. The question's saying, what's the velocity of the top of the ladder? So the top of the ladder is moving down here, right? So the velocity of the ladder is making y smaller. So the y prime is what the question's asking for. So I'm not sure what y is yet, but I know y prime is what I'm trying to find. So we just have one more thing to fill in. We need to fill in the y, and then we'll be able to solve for this y prime that the question's asking about. Okay, so we got to figure out a number to fill in there. And the way we're going to figure that out is, at the moment the problem's talking about, that's a 24. And so we can use Pythagorean Theorem to figure out what the y is at that moment. So y squared plus 24 squared equals 26 squared. That's 576. So minus 100, or sorry, minus 576, and you get 100. Take the square root, you get positive negative 10. Of course, the positive 10 is the one that applies in this case. So now I can come over here and put a 10 here. So 2 times 24 times 2 is 96. Subtract the 96 over. You can figure out the final answer by taking 96 divided by 20. So the y prime comes out to negative 4.8. So what would the label on that be? Feet per second, good, because y is in feet. And so then y is changing in feet per second. And then does it surprise you that the y prime is negative? No, because the y is getting shorter, right? As the ladder falls down, the y is getting shorter by 4.8 feet per second. Now, I said it kind of in a way that made it sound like not an instantaneous rate, but that's an instantaneous rate. That means as the ladder's falling, right at the moment when this is 24, this speed is 4.8 feet per second. But it could be a different speed later. Yes, sir. Yes, thanks. Got some pictures for you. Okay, so everybody okay with this problem so far? So the new idea today is we're trying to figure out how fast things are changing within a picture. So we're trying to see, hey, the rate of this, how does that affect the rate of this? So the rate of this is 2 feet per second, and the rate of this is 4.8 feet per second. So we're seeing how the rates relate to each other. So it's called related rates. So last week was optimization. This week is related rates. Okay, so the next one's example B, so we'll look at that next. It says a conical tank with vertical axis of symmetry of open at the top and with a vertex at the bottom. I don't want to think about those words too much. They basically mean that the cone is pointing downward. This is a conical tank. That means it's in the shape of a cone. And I don't know if the cone is funny or not, but if it is, it's a conical tank. I know I'm not funny, that's for sure. You could read that and think it's a comical tank. That's an N, it's not an M. Okay, so a conical tank with vertical has base radius 4, so that means the radius here is 4. and altitude 10. So the height is 10. And water's flowing into the tank. So there's like a hose or something at the top here. They're pumping water in. Water's flowing into the tank at 9 cubic feet per minute. So that's a prime, isn't it? The 9 cubic feet per minute is how fast something's changing, right? What's changing at 9 cubic feet per minute? Say that a little louder. The volume, right? The water's coming in and changing the volume of water that's in there. So this is V prime. It's how fast the volume of water that's in there is changing. Okay, and then it wants to know how fast is the level of the water rising when the water is 5 feet deep. So what happens is some water flows in, and maybe it fills to this height. And so there's some water sitting in the bottom there. But then later, more water flows in, and so maybe water is filled now to that height. So really what we care about is the volume of the water that's in the tank. So we need a formula for the volume of the water. Because we already have how quickly the volume's changing. So we need what the volume is. Okay, so in that tank, what shape is the water? It's also making a cone shape, right? See the water sitting in there? That's also a cone. It's a cone of water rather than the whole cone. So there's a cone of water down there, and then later there's a cone of water up there. So the volume of the water, we can use the formula for the volume of a cone. And that's 1/3 pi r squared h. Okay, so this is just the volume formula for a cone. And it's, in this case, it's the volume of the water. It's not the volume of the full tank, because that's not changing, right? What is changing is the volume of water that's in there. Okay, so you have a choice. We really need to get a V prime, right? Which means we need to take the derivative of this. And you have a choice. You can take the derivative right away, and then you'd have to use product rule. Or you can try to get rid of one of the variables first, and then take the derivative later. So I think that's a little easier to do. So we're going to go off to the side. We're going to try to come up with a formula that'll get rid of the r and the h. Or get rid of the r or the h, one of them. Okay, so in order to figure that out, so h represents the height of the water, right? And r represents the radius of the water. And at first, it's pretty small. There's an h and an r that's pretty small. See that triangle sitting in there? But then later on, the h is bigger and the r is bigger. So later on, the picture looks more like this as the water level rises. And then when the tank is full, what's the h? 10, right? And the r is 4. So there's a third picture when it's full, but why don't I just put that here, and you'll get what I mean by that. So this is the full tank. 10 for h and 4 for r. Okay, so in all of these triangles, this is a right angle. And this angle at the bottom here is just this angle at the bottom of the cone. So this angle is equal to that angle. And so we have two triangles that have two pairs of equal angles. So this is going way back, 4 years back, but 4 years ago in geometry you learned that if two pairs of angles are equal, then the triangles are similar. So that was called angle-angle similarity. Sorry if I'm bringing back bad memories, but you did proofs with this, and this is your reason. You got to the end and you said, hey, this triangle has two pairs of angles equal with this triangle. And so that's enough to prove that the triangles are similar. Okay, so since these triangles are similar, that means that their side fractions are equal to each other. Their sides are proportional. So if I set up the fraction r over 4, it's going to equal the fraction h over 10. So we proved that the triangles were similar because there were two pairs of equal angles. And then because we know that the triangles are similar, we can set up this proportion. Because similar triangles have proportional sides. So then you cross multiply that, and you get 10r equals 4h. And then you get r equals 4/10 times h, which could reduce to 2/5 times h. So the purpose of all of that was now I can take that mess, 2/5 h, and plug it in over here for r. So now I've got volume equals 1/3 times pi times 2/5 h squared times h. So that's volume equals 1/3 pi times 4/25 h squared times h. And so then that is 4/75 pi times h cubed. Okay, so I just did all of that to eliminate one of the variables. But I still just have a formula that's about volume, right? So I could calculate the volume of this small bit of water, or later on, after it fills up more, I could figure out the volume of the large amount of water. But it still is just an equation about one of those times. It's an equation about either the small volume or the big volume. What I really need is an equation that talks about how things are changing, how quickly this is changing to this. And so I get that by taking the derivative of this. So now I'm going to take the derivative. And the question talks about the change per minute. So that's why I'm doing d dt. Okay, so derivative of v is just v prime. And then the 4/75 pi, that's just a number. So that's nice because it comes out in front of the derivative. It just carries down. Remember, the derivative of a constant times a function is just the constant times the derivative. So I can just carry down the 4/75 pi. And then the derivative of h cubed is 3h squared times h prime. Where does the h prime come from again? Disguised chain rule, right? H is changing as time goes by. The h is this, and then later it's that, right? So since h is changing as time goes by, there's some sort of an equation that tells you how big h is after a certain number of seconds. And that equation is sitting inside of h there. So it doesn't look like chain rule, but it is chain rule because there's a mess inside of h. That's where the h prime comes from. Okay, so this is good. Now we have a dynamic equation. Now we have an equation that talks about how things are changing. And we can fill in what we know into that. We got our v prime, right? That's 9. And let's read the question again. The question says, how fast is the level rising when the water is 5 feet deep? So it's talking about the water level. So that's the h. And it's talking about how fast the water level is changing. So how fast h is changing. So the question's asking for h prime. So I know I don't have that. So I guess I got to figure out what h is. Well, it says, how fast is the level rising when the water is 5 feet deep? So if the water's 5 feet deep, that means the height of the water is 5 feet. So we put a 5 there. And then you just multiply all that out to solve for h prime. So 9 equals 4/25 pi times 75 h prime. Five squared is 25, and then 25 times 3 is 75. That's where I got that. Then that's nice. The 75 and the 25 just come out to 3. So that's 9 equals 12 pi times h prime. So then h prime is 9 over 12 pi. And that would be in feet per second. Or sorry, not per second, per minute for this problem. Yes? Oh, I just messed up, didn't I? Sorry. Thanks. Miss couldn't read my own writing, so this would be a 4 pi. Thank you. And this would be a 4. Sorry about that. I had a 75 here, and then I turned it into a 25 there. Not sure why. Should have been 75, 75. And so then the 75s go away, and you just have 4 pi times h. Okay, so remember, at the beginning, we could have taken the derivative without plugging in, but it would have been then a product rule problem, and it would have been tougher to take the derivative. So my advice is to try to get rid of one of the variables before you take the derivative. It just makes it a lot easier. Is everybody okay with example B? Are you sure? Okay, moving on to C then. Okay, so in example C, we've got a man, 5 foot tall, walks at the rate of 4 feet per second directly away from a lamp that is 15 feet above the ground. And the question says, find the rate at which the end of his shadow is moving when he's 30 feet away from the lamppost. All right, so we've got the ground and a 5 foot tall man. And then there's a lamp over here with a light at the top of it. And the lamppost is 15 feet tall. Okay, so what happens is the light shines on the man, right? And the man blocks the light. And so then there's darkness over here. That's called a shadow. I can really overanalyze anything, can't I? darkness on the ground caused by someone blocking light, that's called a shadow. Okay, so but what happens is some of the light just barely escapes above his head, right? And then over here, light escapes. So the shadow is going to be here because the blockage of the light happens there. So I'm going to call that S for shadow, which is a little bit dangerous because it kind of looks like a 5, but then there's light up here. Okay, then also the man is walking away from the lamp, right? So the distance from the lamp to the man is changing. So I need to call that x. So x represents the distance from the lamp post to the man. Okay, now we have to come up with an equation that talks about this picture. So there's a large triangle. That's this one. That's x plus s on the bottom and 15 on the side. And then there's a small triangle. That's 5 here and s on the bottom. So that's this triangle. These are both right angles. We're going to assume that the man has really good posture and that he is standing up at a right angle. And the lamppost is also very well installed. So it's at a 90-degree angle. So both of these are 90. And then this angle appears in both triangles, right? It appears here and it appears there. So again, we have similar triangles. They're similar by angle-angle similarity. Because there's two pairs of angles that are equal. Okay, so since the triangles are similar, we can set up proportions with the sides. So 15 over 5 equals x plus s over s. So this is a 5. These are s's. So then I'm going to cross multiply that. So 15s equals 5x plus 5s. And then subtract the 5s over. So 10s equals 5x. So this equation right here is a static equation. It's just about one moment in time. So I'm going to take the derivative of it to create an equation that talks about how things are changing. So the derivative of 10s, well, let me start with 5x because that's easier for people because they like x. Derivative of 5x is 5. But then it's a disguised chain rule, so it's times x prime. Normally, the derivative of 5x is just 5, right? But since it's d dt, it's 5 times the x prime. Okay, then for the 10s, it would be 10 times s prime. Okay, so what other information do we have in here? He's walking at a rate of 4 feet per second. So he's walking. Here's where he is. He's walking this way at 4 feet per second. So that's making x bigger, right? As he walks at 4 feet per second, the x gets larger by 4 feet per second. So the 4 feet per second is the x prime. So then S prime is 2. So what does that mean, S prime is 2? What did S represent? The length of the shadow, right? So S prime equals 2 says what? It says that the shadow is getting bigger by 2 feet per second, right? So that's good information. The shadow is getting bigger by 2 feet per second. You've noticed that, right? When you're walking, when you were a little kid, you're like, hey, look, my shadow's taller than yours. Because the shadow was getting bigger as you walked away, right? Okay, so the shadow length is changing. If you're out here, it's going to cause a lot bigger shadow, right? So that's what the shadow... Okay, is this what the question's asking, though? Does the question say, how fast is his shadow growing? No, it says, find the rate at which the end of the shadow is moving. Okay, so let's think about this. The lamppost is over there. I'm walking this way, right? The shadow is moving for 2 reasons. Look at the end of my shadow over there. The shadow is moving for 2 reasons. Number 1, it's moving because I'm walking. And so when I walk, that causes the shadow to move, right? But the other reason the end of the shadow is moving is because the shadow is getting longer. So the shadow is expanding at a rate that's faster than I'm walking. I mean, it includes my walk rate, but it also includes the lengthening of the shadow. Okay, so I need to know how fast is this point moving, the end of the shadow. And this point is x plus s away from the lamppost, right? So x plus s represents how far the end of the shadow is from the lamppost. And I want to know how quickly that's changing. And when you take the derivative of 2 things added, you just take the derivative of the first thing plus the derivative of the second thing, right? So x prime is 4, and s prime is 2. So that means that the x plus s prime is 6 feet per second. Keep saying seconds. Yeah, this one's back to seconds. Okay, good. So the x plus s prime is 6 feet per second. So the x plus s is the distance from the lamppost to the end of the shadow, right? And what's happening is that's getting longer by 6 feet per second. So that means that this point is moving 6 feet per second because this point is not moving. So if this gets longer by 6 feet every second, then this is moving at 6 feet per second. So the end of the shadow is moving at 6 feet per second. Is everybody okay with that? Okay, so what this was about was just pointing out that the end of the shadow is moving for 2 reasons. It's moving partially because the man is moving, and it's also moving partially because the shadow is getting longer. And altogether, that's increasing at 6 feet per second. Yes? So Jesse's pointing out that there's a 30 in the problem that we never used, right? Apparently, it doesn't matter how far away the man is from the lamppost. Apparently, that doesn't affect how quickly the shadow is moving. And so that 30 was the x, right? And so notice that when we took the derivative, the x went away. And that's why apparently it doesn't matter. So here's a lamppost, here's a person. It doesn't matter how far away from the lamppost you are, that doesn't affect how quickly the shadow is moving. And that's why we didn't need it. But it's in there so that somebody will ask this question. And so then we can talk philosophically about the fact that, oh, the x went away, and so it doesn't matter. Thank you for listening.